Welcome to a lesson with Dr. Powell. Let's take a look at a concept called orthonormal. It describes a type of basis. It is a basis which is orthogonal, and each vector in that basis has length 1. Another way of saying orthogonal is that the dot product between any two vectors is 0, and length 1 is the dot product of each vector with itself is 1, because that's the sum of the squares, and the length is the square root of the sum of the squares. Here's an example. E1, E2, E3, the standard basis of our 3 is an orthonormal basis. Each has length 1, and they're all orthogonal to each other. Here's a basis for a subspace of R4. If you take a dot product of any two of these guys, you get 0. The length of this guy is that squared plus that squared plus that squared plus that squared, which is a half plus 0 plus a half plus 0, which is 1. Okay. Let's take a look at some consequences of things being orthonormal or orthogonal even. Let's start with orthogonal. We have a consequence. If vectors are orthogonal to each other, then they will be linearly independent. Let's take a look at that. Let's suppose that we have some vectors that we put as columns in a matrix A. Now, if we took the transpose of this matrix and we multiplied them together, what happens? Well, here's a little block matrix multiplication to help us. Let's block by rows here and by columns here. Now, notice that we didn't do any column partition at all over here, which means we must not do any row partition over here to make this work. So we have, but we can partition it any other way we want. So we can do rows and we can do columns, and the effect is to kind of put the results in the respective places here in this matrix. So we have this row. So what comes from this row and this column, which is this right here, would be our first entry. Then this row and that would be the second entry. This row and that would be the third entry. Or you could just simply think of it this way. We made blocks and then just matrix multiply it. That's like saying so just matrix multiply it. So we have this row, right? So you have this, this row, and suppose it just has one thing in it. So it's like one thing times that row, and that'll be the first row under a row interpretation. Or we could think about a column interpretation. We just say this one guy times that column. So V1 times all that guy, V2 times all that guy, V3 times all that guy. However we want to think about it, we get this nice matrix. All right. Now look at what these are. This is a row, column. These are dot products right here. Now all these dot products up here off the diagonal are 0 because they're orthogonal. These are 0. And down the middle, these are non-zero because a vector dotted with itself is the square of its length. And the only way for a vector to have length 0 is for it to be the 0 vector. So therefore, none of these dot products are 0. In fact, in this case, you see what they are. There's 2, 1, 3. In fact, they're going to be positive numbers because it's a sum of squares. So we have 2, 1, 3 in this particular case as dot products. Now this brings up an interesting point. You see these things, 2, 1, 0. What if it was orthonormal? This would be a 1, 1, 1. Oh my goodness. That would mean that AT, in fact, would be a left inverse to A if these happen to be orthonormal. Okay, so how can you make a set of vectors orthonormal? Well, you simply just divide by the length. So in other words, what if I came here and I just divided by the length of this vector? The length of this vector is the square root of 2, because you say 1 squared plus 1 squared and square root. So just divide out by square root of 2. Okay. This vector has length 1. This vector has length square root of 3. Because you have 1 squared plus 1 squared plus 1 squared, take a square root. So do that. Okay, then over here, let's modify this so it's still a transpose. So we get that, and over here, and let's see what happens now. When we matrix multiply this out, you'll actually see you get a third plus a third plus a third. That actually becomes 1 because it's a dot product, right? dot product of that, and this has length 1, so its dot product will be 1. So basically the dot product of all of these guys, which is 1, 1, 1 now, because their length is 1, and you can double check it to make sure, but you get this, the identity matrix. So sure enough, if these columns happen to be not just orthogonal, but orthonormal, then we don't even just get linearly independent, but we get a nice way to find inverses. So if the columns are orthonormal, then what does that mean? So the columns are orthonormal, then that means that we have that the transpose right here is an inverse. Okay, and in this particular case, we have it being a left inverse. Now, if we put a transpose on the other side, let's see what would happen. With that, so if we put a transpose on the other side, then let's see, thinking about that. So running that through, just imagining what that would be like. So like this dotted, notice that it's the same. You can check it, but it's the same. It's the exact same setup. This guy dotted with, so this row dotted with this particular column, right? It's not necessarily going to be as nice here in that sense, because you have what, a half plus a third. That doesn't give you 1. If you take that dotted with that. So it's not, so it doesn't look like we're going to be getting an inverse that way. But still, orthogonal columns in this case give us something very nice, with the transposes being a left inverse. Okay, but what if we had a square matrix? All right, square matrix. Okay, so let's change this setup to a square matrix. So what if A was this, but to make it orthonormal, we would need to put on a, let's put a 2 here and a 2 here, okay? Like that in that way, okay? And let's take a look at what happens. Let's see, what needs to change before I erase anything? Okay, so we have, in this particular case, what do we got? We got rows. Okay, so this row becomes that column, that column, okay? So yeah, so we need to modify. Let's just go like that. So that's going to be square root of 2. That's going to be square root of 2. Okay, like that. And I think we got it, right? So first row is there, second row is there, and third is there. Okay, then when we dot this, notice, okay, so of course we should have the same setup just because of this, but also realize that these are transposes of each other. So this argument would be extremely symmetric. In that case, we'd still have the same size of matrix based upon these guys right here, and each one of these would yield a single element, and these would still be dot product. Yeah, these would still be dot products. So we'd have a different setup if we weren't able to replace this by 3 and 3 in the same kind of way as we were doing here. Okay, so for square matrices, actually, orthonormal rows, orthonormal columns both give you this idea that the transpose is the inverse. Kind of nice here. This is for square matrices, though. However, you do still get a nice fact for with it either being a left inverse or perhaps if you change the situation, maybe even a right inverse if you kind of worked with it a little bit. Um, in that case, for orthonormal, maybe if you're looking at orthonormal rows or something like that. But orthonormal bases can help us think about inverses. And here were just a couple examples of that idea. Thanks for watching.